Hi everyone, in this video we're going to talk about array lists. Now at the beginning I'm going to highlight some of the important differences between arrays and array lists just as a matter of some context, but the most important information has to do with the implementation of array lists. So as a point of review and just to set up some context, let's think about how arrays and array lists differ. So an array, the most important thing to know about an array is it's a fixed size. It can't grow, it can't shrink. You create an array with 100 elements in it, and later you decide you need to store 101, you're out of luck. There's no way to do that. The other thing you'll notice as you use an array is that you're primarily using that common square bracket syntax to get and put elements. Now, for point of comparison, you can have arrays of primitive data. We can have an array of ints or doubles, characters, booleans, and so on, where you can't with an array list. The other thing is array lists are by their very nature very simple. That holds data, you use the square brackets to put data in and get data out, but there isn't any other methods to speak of like there are with array lists. Now, an array list is just a class that wraps up an array. Arrays come from the very beginning days of computer science before we had the idea of object-oriented. An array list is an object. So it does what an object does. It has instance data, which is that array, and then provides methods to act on that instance data. Now, because of that design, array lists can appear to change their size. And the way they do that, we'll look at this in more detail, but to do that they have to delete the old array and create a new one, because of course we still can't change the size of arrays. But since the array list is a wrapper around the array, we don't see what goes on in the middle, so to the casual user it looks like the array grew, which is typically the behavior we want. Array lists cannot directly hold primitive data. You have to use those wrapper objects. So if you want an array list of integers, you have to use the integer class with the capital I, and that's not anything to do with the concept of an array list itself. That has to do with the way that generics work in Java. Because array list is a generic class, then it can't hold primitive data. You could, in theory, write an integer array list class that only worked for integers. But that would involve a lot of cut and paste type of code, so the designers of Java use the wrapper classes instead. And because ArrayList is a class, and in line with the model of object-oriented design, it provides a bunch of convenience methods, right? We want those operations on our list of data, things like clear or contains or index of, or if you go to the API, there's a whole list of things here you can do to an array list that you can't directly do to an array. You'd have to write your own code. Okay, so with that as a setup, let's look at a couple of the key inner details of arrays and array lists. All right, when we create an array in any language, this is just the basic idea of an array, what you get is a section of memory used to hold a bunch of elements. So for example, if I create an int array in Java, we'll call it array, of size 100, then the operating system allocates 100 slots in memory for those 100 arrays, and it puts them all next to each other. And this is what makes arrays so efficient to access, is when I say like array slot 6, it's a simple addition. We remember for the array the memory address at the beginning, and then we just add 6 to it to get to the particular slot we want. That gives us our big O of 1 access. The trade-off for that design is that we can't grow the array. If I decide I now need to store 101 integers, I can't necessarily do that because this spot right here where the 100th and first integer might go could potentially be used by something else. When we created the array, we sectioned off 100 slots. We didn't claim any other territory, so in the meantime something else may have come along and used up that spot. That's not to say we couldn't invent a clever computer, an operating system, and memory system that would move stuff around, but over the years we've learned that that's just trading one problem for another, and in fact trying to move stuff around in memory opens a big can of worms that usually doesn't pay off in the long run. So that's why arrays can't change size. We don't want to assume that there's room around the array to do that, it makes other things too difficult. Now, an array list is just a wrapper for an array, and that lets us appear to get around some of those problems. So if I create a new array list of strings, then what I get is I get my ArrayList object, and one of its instance values is just a reference to the array we're going to use. This array, of course, is of fixed size because arrays have to be of fixed size, but because it's wrapped up inside of the object, the users don't directly interact with this private instance variable. So if we ever decide we need more room, we have the flexibility of replacing this array with another one. So conceptually what we do is we create a new array, a new bigger array, that would go somewhere else in memory where we know we have all the room we need. Then we'll copy the data over, and then when we're all done, we can change the reference to the new array. So from the outside, it looks like our array is grown. What we've really done is replaced the insides. It's like if I took my car to the shop and the mechanic pulled out my 2.0 liter engine, put a 2.5 liter engine in. It looks like the same car. I get in the car, I interact with it the same way, but something has changed under the hood. And I don't even have to know that that's happened, although I'll get a bill for it, but you get where I'm going with the analogy here. Okay, so let's take a look at the code that does that. Okay, so this is the actual source code for ArrayList.java. You see, comes from Oracle, has lots of comments in it. Some things to notice. One, the instance data, right? The instance data for this array list is an array of whatever we're going to hold, and another instance variable that keeps track of the size. Everything else is just operations on those instance variables. So the interesting thing to notice is what happens when we need to make more room. The method that does that is called ensure capacity. It makes sure that the array has a certain amount of room in it. So when we do that, first we check to see, okay, do we need more room? If we don't need more room, there's nothing to do. And then we take that instance variable that's currently holding our data and we copy that reference into a different instance variable. So now we have two references to that array. And now we need to decide how much to make that array grow. So in this case, it grows by 150%, 3/2. And then this instance variable, that array, gets set to a new object. So we're going to create a new array. So we're changing that reference. And then we copy the old data into the new data. Now there's a system.arrayCopy method that does that, but really it's just a for loop. Under the covers, it's a fancy for loop that just goes through index by index and copies the data from the old data to the new data. Now to see where we might grow the array, look at the add method. This is what adds an element to the end. The first thing it's going to do is make sure that it can hold one more element than it currently has. So if it can, nothing happens. If it can't, you just saw what happens above, and then we can put the element in there. There's other methods in here that are going to ensure capacity as well. But the key idea, of course, is that we end up with a new array with the old data copied into it. Now the interesting question is, how much extra space do we put in this new array? What we saw here is that Java makes it grow by 150%. The 3/2 right here. Why is that? And that's what we're going to focus on for most of the rest of the video. First question, what is the big O running time of the ensure capacity method? Assuming it grows, of course. And the answer to that is big O of n, right? If there's n elements in the array, all n need to be copied. So to copy that is a linear time operation. So let's imagine that our array list starts out empty and only grows by one element at a time. Okay, and then we have a loop something like this. Let's say we have a for loop for I equals 0, I is less than some size n, and then we'll take our array list and we'll add that element to the end of the list. So what this will effectively do is every time we add an element, then we have to do a copy. Okay, so let's take our item. So we'll put in item 0, item 1, item 2, and so on. And for each item, we'll look at the cost. So the cost of putting item 0 in is 0. There's nothing to copy. The cost of putting item 1 in, we have to copy one thing. Before we put item 2 in, we have to copy 2 things. Before item 3, we have to copy 3 things, 4 things, and so on. So if we add up all of these costs, it ends up being 1 plus 2 plus 3 plus 4. We've seen this before, right? And now up to n minus 1 plus n. Right? The cost of adding the next item is 1 more than the cost of adding it before. And we add all of those up, and we've seen that this ends up being big O of n squared. So the cost of this loop right here, if the array grows 1 at a time, that total cost would be big O of n squared. Now, let's again assume that the array list begins empty, but that the size doubles every time we enter an element. So we're going to do that same for loop. We're going to put things in 1 at a time. And now let's look at what that relationship looks like. So we'll again have our item and we'll have our cost. So when we put item 0 in, there's no cost, there's nothing to copy, and we'll just create an array of size 1, and we'll put 0 in it. But since we're not copying anything, we'll just count that cost as 0. When we put item 1 in, this array is full, so we have to rebuild the array. So we create an array of size 2, but one thing has to be copied, so that has a cost of 1. And we'll put 1 in there. Now we want to put item 2 in the array. The array is full. So we'll create an array of size 4. We're going to double each time. We only have 2 things to copy though, so we'll copy the 0 and the 1, and then we can put the 2 in. We go to put item 3 in. There's no cost there because there's already room for the 3. We go to put item 4 in. We'll double the array. So now there's 8 spaces in the array, but we have to copy 4 things. So now when we put item 5 in there, there's already room for 5. There's already room for 6, so there's no cost there. There's already room for 7, so there's no cost there. But when we go to put item 8 in, we're out of room, so we've got to double the array again, and we have to copy those 8 elements. And then we can put element 8 in there and so on. All right, so do you see the pattern? Where do we have a cost? Our cost is all at powers of 2. So at 2 to the 1, there's a cost of 2 to the 1. At 2 to the 2, there's a cost of 2 to the 2. At 2 cubed, there's a cost of 2 cubed. Right, there should be an 8 there. And everywhere else, there are zeros. All right, so what? Let's see what that does for us. Let me draw this pattern out again. So we've got a 0 with a 0 cost, 1 with a 1, 2 with a 2, not a power of 2. All right, so how does that cost add up over time? So if we put n things into the array, what would be our total cost? And so here's the key observation. When I pay a cost of 2, so I use 1, and there's a free space. When I pay a cost of 4, I use 1 right away, and then it's followed by 3 zeros. When I pay a cost of 8, I use 1 right away, and it's followed by 7 zeros. When I pay a cost of 16, it would then be followed by 15 zeros. So when this all averages out, each addition is just paying a cost of 1. So we have a cost of 1 per addition on average. Because, for example, at the point where we added the fourth element, we paid a cost of 4. What we did was we paid for ourselves and the next 3. When we paid a cost of 8, we paid for ourselves and the next 7. So it averages out to each addition only paying 1. So that means the total cost of n adds is just n. So that gives us a big O of n behavior instead of a big O of n squared behavior. Okay, to summarize, if we grow by 1, then the total cost for n additions is big O of n squared, which means the average per addition is big O of n. If we grow by double, the total cost of n adds is just n, which gives us an average per add of big O of 1. And obviously this is a big win. So even though making the array grow has the potential to be expensive, by being smart about how and when we grow, we can still get that constant time behavior that we look for in an array implementation. Now, notice here, when I did this example over here, I doubled the size of the array as opposed to growing by 150% because it makes the math work easier, but the principles are the same. I'll leave the math for the math class or the data structures class, but the spoiler is to get this behavior that we want, we just have to grow by a percent. It doesn't really matter what the percent is. So if you grow by 10%, 20%, 50%, 100%, the percent doesn't matter. The fact is that you're growing by a percentage, whereas if you grow by a constant amount, you'll eventually get the slower behavior you don't want. So it doesn't matter. You can grow by 1, you can grow by 10, you can grow by 100, you can grow by 1,000. They'll all eventually devolve into that big O of n behavior you don't want. Another way of saying this is you want your growth to be proportional to the size of the array. So as the array gets bigger, you want to grow by more. Now, how do you decide whether you're going to grow by double or by 150% or whatever it is? I don't know that there's a theoretical optimal there. You're just making a trade-off between the amount of time you spend growing your array and the amount of extra RAM you're using. If you grow too big, then you're taking up memory that doesn't get used. If you grow too small, then you spend extra time growing your array. There probably isn't a right answer globally, but over the years, those at Java have discovered that 3/2 seems to work well in practice. I hope you found that peek under the hood at Arrays and ArrayLists interesting. I know it's the kind of thing that kept me hooked on computer science. I didn't go into some of the gory details because it doesn't necessarily apply to 163 as a whole, but certainly I can empathize with any of you who like that stuff, and I'm happy to talk about it. I love to geek out on the inner details of computer science, so feel free to stop by or ask questions if you're one of the ones who really likes to see those inner workings.